Welcome to Robotics Lecture 14. This is your Professor Atif Fareed Muhammad. Robot programming is essential for automation and control. It involves creating instructions for robots to perform tasks. This field combines software engineering and mechanical systems. In a nutshell, robot programming is a cornerstone of modern automation and control systems, playing a pivotal role in various industries by enhancing efficiency, precision, and productivity. It involves the development of detailed instructions and algorithms that enable robots to execute specific tasks autonomously or semi-autonomously. This interdisciplinary field merges principles of software engineering and mechanical systems, requiring a robust understanding of both coding and mechanical operations. By creating sophisticated programs, engineers can dictate the movements and decisions of robots, permitting them to perform complex operations, ranging from assembly line tasks in manufacturing to intricate surgical procedures in healthcare. The integration of software and medical and mechanical engineering not only optimizes the performance of robotic systems, but also ensures their reliability and adaptability in dynamic environments. One notable example of robot programming in healthcare we can take is the Da Vinci surgical system, which exemplifies the transformative potential of robotic technology in medical procedures. The Da Vinci system consists of console used by the surgeon to control robotic arm equipped with surgical instructions and instruments working in tandem. Through advanced programming and precise control algorithms, the system translates the surgeon's hand movements into smaller, more precise movements of the instruments inside the patient's body. This robotic assisted surgery enhances the surgeon's capabilities, permitting for minimally invasive procedure that reduce patients' recovery time and improve surgical outcomes. The programming behind such systems involve real-time data processing, sophisticated motion control, and integration of feedback mechanisms to enhance and ensure safety and accuracy. Robot programming languages are specialized for robotic tasks. They facilitate communication between humans and machines. These languages are vary based on the complexity of the robot's tasks. Let's look into this with an example. One prominent example of a specialized robot programming language is the Robot Operating System, or ROS, Industrial, which is widely used for programming complex robotic tasks in industrial settings. ROS Industrial extends the capabilities of the open source robot operating system by providing libraries, tools, and functionalities tailored for industrial robotics applications. This language facilitates seamless communication between humans and machines, enabling engineers to program robots for tasks such as welding, material handling, and assembly with high precision and flexibility. ROS Industrial supports a wide range of robotic hardware and integrates various sensors and actuators, making it a versatile choice for automating complex industrial processes. Efficient robot programming enhances productivity and precision. It is crucial in manufacturing, healthcare, and exploration. Proper programming ensures safety and reliability in operations, as we discussed earlier. The complexity of tasks that a robot can perform often dictates the choice of programming language. For instance, simpler tasks like pick and place operations might be programmed using more straightforward proprietary languages provided by robot manufacturers such as KUKA's KRL or KUKA robot language or ABB's Rapid. These languages are designed to be intuitive for specific robotic systems and are optimized for ease of use in programming repetitive tasks. In contrast, more complex tasks that require advanced decision making, sensor integration, and real time adaptability often utilize more sophisticated languages like ROS or even general purpose languages like Python and C++. These languages offer greater flexibility and a broader range of libraries for handling intricate operations, thus catering to the diverse needs of modern robotic applications. The first level involves low-level programming. There are 3 levels. And direct hardware control. It deals with basic movements and sensors feedback. Programmers often use assembly language or embedded C. The second level focuses on control algorithms and motion planning. It involves more complex tasks like pathfinding and obstacle avoidance. Languages like C++ and Python are commonly used here. The third level is high-level task planning and artificial intelligence integration. It involves decision-making and autonomous behavior. High-level languages and frameworks are utilized for these tasks. Let's look into this with a couple of examples. Since we have discussed the third level of robot programming, which involves high-level task planning and artificial intelligence integration, is crucial for enabling robots to perform complex autonomous behaviors. This level focuses on decision making, as discussed earlier, processes of decision making that allow robots to adapt to dynamic environments and perform tasks with minimal human intervention. High-level languages and frameworks such as Python, with its extensive libraries for AI and machine learning, are commonly used to develop these sophisticated systems. These tools provide the necessary flexibility and power to implement advanced algorithms for perception, planning, and control, enabling robots to operate autonomously in various applications. One example of high-level task planning and AI integration is seen in autonomous mobile robots used in logistics and warehouse management. These robots are programmed to navigate large dynamic environments, avoiding obstacles and efficiently transporting goods from one location to another using frameworks like the robot operating system, as mentioned earlier, in conjunction with the AI algorithms. These robots can make real-time decisions based on sensor data and predefined task objectives. For instance, an autonomous warehouse robot might use simultaneous localization and mapping, or SLAM, techniques to build a map of its environment while keeping track of its position. AI integration allows the robot to optimize its path, avoid collision, and adapt to changes in the warehouse layout, thereby improving efficiency and reducing the need for human oversight. Another example is found in the field of service robotics, where robots are designed to interact with humans and perform tasks in unstructured environments. A prominent illustration is the use of social robots in healthcare settings, which assist with patient care and support. These robots leverage AI to understand and respond to human emotions, recognize speech, and make context-aware decisions. High-level programming languages and AI frameworks enable these robots to integrate data from various sensors and cameras, process natural language, and engage in meaningful interactions with patients and healthcare providers. For example, a social robot might use machine learning models to analyze a patient's facial expressions and tone of voice, permitting it to provide personalized support and companionship. By integrating AI with high-level task planning, these robots can autonomously perform a range of tasks, from delivering medications to facilitating telehealth consultations, thereby enhancing the quality of care and operational efficiency in healthcare facilities. Industrial robotics or industrial robots are widely used in manufacturing and assembly lines. They perform repetitive tasks with high precision and speed. Programming these robots involves both low and high level instructions. Medical robots, as discussed earlier, assist in surgeries, rehabilitation, and patient care. They require precise control and real-time feedback mechanisms. Programming these robots often involve advanced AI techniques. Service robots, as discussed earlier, are used in domestic, entertainment, and customer service environments. They need to interact safely and effectively with humans. Programming focuses on user interaction and adaptability. A robot programming language must support precise control of movements. It should handle real-time data processing and feedback. Accuracy is critical for tasks requiring fine motor skills. Let's look into this in a little bit more depth. One example of robot programming language that supports precise control of movements and real-time data processing is UR-Script. Used in universal robots, collaborative robots, or cobots, UR-Script allows for detailed programming of robotic arms, enabling them to perform tasks that require high precision, such as assembly, picking, and placing small components. The language provides functions to control the speed, acceleration, and force of the robot's movements, ensuring that tasks are performed accurately and safely. Real-time feedback mechanisms in UR-Script allow the robot to adjust its actions based on sensor data, which is crucial for applications requiring fine motor skills and adaptability to dynamic environments. Another example is KUKA robot language, or KRL, as mentioned earlier, specifically designed for KUKA industrial robots. KRL, it's also known as KRL, facilitates precise control over robotic movements, as mentioned earlier. And since we have discussed the ABBs, our rapid programming language, let me explain a little bit more in depth. It is tailored for precise control and real-time data processing in industrial robotics. Rapid is used to program ABB robots for a wide range of applications, including painting, assembly, and packaging, where accuracy and fine motor skills are paramount. The language includes features for motion control, such as path planning and coordination, which enable the robot to execute complex movements with high precision. Additionally, Rapid supports real-time feedback loops, permitting the robot to continuously monitor and adjust its actions based on input from sensors and other external sources. This ensures that the robot can perform tasks with the required level of accuracy and adaptability, making it a valuable tool in industrial settings where precision is critical. The language should be flexible to adapt to various robotics applications. It must support modular programming and easy integration with sensors. Flexibility ensures the language can evolve with technology. Let's look into this with an example. One exemplary language that embodies flexibility and adaptability in robotics applications is Python, particularly when used in conjunction with Robot Operating System, or ROS. Python's simplicity and readability, combined with its extensive libraries and frameworks, make it an ideal choice for the wide range of robotic applications, from simple educational robots to complex industrial systems. Its support for modular programming allows developers to create reusable code modules which can be easily integrated and adapted for different tasks and robot configurations. This modularity not only streamlines the development process but also facilitates the integration of various sensors and actuators, enabling robots to interact effectively with their environments. Python's flexibility ensures that it can evolve alongside advancements in technology, as new sensors, algorithms, and hardware components are developed. Python's extensive ecosystem allows for seamless integration and experimentation. For instance, libraries such as NumPy and SciPy provide robust tools for data processing and scientific computing, while TensorFlow and PyTorch offer powerful capabilities for implementing machine learning and AI algorithms. This adaptability makes Python a future-proof choice for robotic programming, capable of accommodating the ever-changing landscape of technical innovation by supporting a wide range of applications and fostering an environment of continuous development. Python exemplifies the importance of flexibility in robotic programming language. Safety features are essential to prevent accidents and ensure reliable operation. The language should support fail-safes and error handling mechanisms. Safety protocols must be integrated into the programming framework. So we must be mindful when we are working with the robotics programming language to cover all the areas which might not be upfront as we are looking into the research or researching the context-centric need or needs. Real-time processing is a significant challenge in robotic programming. Delays in processing can lead to errors and accidents. Efficient algorithms and hardware are required to handle real-time data. Integrating multiple sensors and processing their data is complex. Sensors provide critical feedback for robot operations. Effective programming must handle sensor fusion and noise reduction. Let's look into this in an example in more depth. One detailed example of the complexity involved in integrating multiple sensors and processing their data can be found in autonomous vehicles. These vehicles rely on a variety of sensors, including cameras, LiDAR, radar, and ultrasonic sensors, to navigate and make decisions in real time. Each type of sensors provide different types of data. Cameras offer visual information for object recognition and lane detection. LiDAR generates high-resolution 3D maps of the surroundings. Radar detects the speed and distance of objects, and ultrasonic sensors assist in close-range obstacles detection. The integration of these drivers data streams is crucial for the vehicle to perceive its environment accurately and make safe driving decisions. The process of sensor fusion in autonomous vehicles involves combining data from multiple sensors to create a unified and comprehensive understanding of the environment. As I mentioned earlier, the context-centric research. This task is complex due to the varying formats, update rates, and accuracy levels of the data provided by different sensors. Effective programming must employ advanced algorithms to align and integrate this data, ensuring that the resulting information is consistent and reliable. Techniques such as Kalman filtering and particle filtering are commonly used to estimate the state of the vehicle and its surroundings by fusing sensor data. Additionally, noise reduction methods are applied to filter out inaccuracies and improve the quality of the data. For instance, noise from sensors measurements can be mitigated using statistical methods or machine learning techniques that identify and correct anomalies in the data. The programming must handle the real-time processing requirements of autonomous vehicles, where delays in data processing can lead to critical errors. This necessitates efficient software architectures and optimized algorithms that can process large volumes of sensor data quickly and accurately. Robust sensors fusion frameworks, such as those provided by the Robot Operating System or ROS, are often utilized to manage the complexity of integrating multiple sensors. These frameworks offer tools and libraries for developing sensor fusion algorithms, facilitating the creation of reliable and scalable autonomous systems. By effectively handling sensor fusion and noise reduction, autonomous vehicles can achieve a high level of perception and decision making required for safe and efficient operation in dynamic environments. Robots must adapt to changing environments, as mentioned earlier, and tasks. Programming must account for unpredictability and dynamic conditions. Adaptability requires advanced AI and machine learning techniques, as mentioned earlier. Robot programming is a rapidly evolving field with vast potential. Future trends include more advanced AI integration in autonomous systems. Continued innovation will drive the capabilities of robotic systems forward. A simple robot programming language, when is opted appropriately, can generate a sample path, and let's look into this in a little bit more depth. So the path storage here shows the path list stores that coordinates of the robot's position after each move. The plot path method I used in this specific program, it uses matplotlib to plot the path. It extracts x and y coordinates from the path and plots then with markers and show each step. The grid is set up with appropriate limits and labels. The y-axis is inverted to match the typical grid representation where 0, 0 or 0, 0 is at the bottom left corner. So I suggest you to conduct a little bit more in-depth analysis of the robotics program that you are writing or you're about to write to create a simulation like this by using the robot move down, robot move left, robot move right, robot move up, and by creating the grid with initial position after moving up, after moving right, after moving left, or after moving down will allow you to find all these details by yourself. Happy learning. Take good care of yourself.